Some people are very focused on having a lot of money. My career has been driven more by curiosity. Follow what you're curious about. Don't care whether you can get a big grant by doing it. In modern society, one of the things that seems to be unbelievably lacking among public figures now is a sense of integrity. And I think that having integrity, believing in what you're doing, and doing things consistent with your beliefs is unbelievably important. And it's hard to believe that many public figures now are acting with any sense of integrity. So I think that that's incredibly important. The importance of being tenacious. So, especially as a basic scientist, there are going to be lots of times when people don't really care about what you're doing or are going to not give you a job. So I think tenacity in my own life, curiosity and tenacity have been really important factors. I'm strongly encouraged to be tenacious and curious. I think it's important to really challenge people with hard problems. I don't know that my children or now my grandchildren are given challenging problems of that sort as part of the educational system. To me, that's something which I think was unbelievably important in terms of my own development.
If you had to summarize your life's mission from the beginning to now in one sentence, what would that sentence be?
Whoa. I've tried to do things that I found enjoyable and to be good and fair to people.
Hey guys, welcome to another episode of Wandering Thoughts. Today I'm joined by Professor Leon Glass. Professor Glass, first of all, thank you for joining us. It's a pleasure and honor to learn from you and talk to you. Tell us a little bit about yourself.
So I am a retired professor of physiology at McGill University. I'm now in California, where I come to escape the Montreal winters.
Okay.
And I've had a fascinating career trying to do applications of nonlinear dynamics and mathematics to study physiological rhythms. I'm fascinated by complex rhythms, and if you have a body, you have a lot of fascinating complex rhythms. So I'm fascinated in those, and I've had a lot of fun trying to understand them and trying to understand them both from a physiological point of view and from a mathematical point of view.
Mm-hmm. Tell me a little bit about your career from the beginning and walk me through it, because it's quite an unconventional path, the path you took. You're an interdisciplinary scientist and you've worked in lots of different areas of science, which is quite unusual for most people, and it's also something that I find very fascinating.
Yeah, well, I always liked biology. I had tropical fish when I was growing up, and I went to college in New York City. I attended Brooklyn College.
Mm-hmm.
I was initially a pre-med major, and then I learned that I was not very good in memorizing the parts of the body, so I did not enjoy comparative vertebrate anatomy. So they recommended that I no longer be a pre-med major.
Mm-hmm.
I was then a psychology major. I was fascinated by experimental psychology and normal psychology.
Mm-hmm.
But then when I got to abnormal psychology, I started getting C's in my courses, and I thought I could do better in chemistry, which I had taken, I had enjoyed. So I ended up being a chemistry major at Brooklyn College. And then I wanted to continue doing academic work. I wanted to go to graduate school. There had been several people from Brooklyn College who had gone to the University of Chicago, including someone who turned out to be my thesis advisor, someone named Stuart Rice, who was only 10 years older than me, but was a rather spectacular scientist who had a fantastic career. And there were two people just in classes in front of me who had also gone from Brooklyn College to University of Chicago and also ended up doing very well. So I went to Chicago, and I did a PhD in chemical physics at the Department of Chemistry in Chicago. And I started out doing experiments, but I realized that I tended to break things. I was breaking some very expensive ultraviolet cuvettes. Each time I did an experiment, I had to lower them into liquid nitrogen. So I was fascinated. One of Stuart Rice's areas was theory of liquids, and I was fascinated by atomic motions in liquids. And that's what I did my PhD on. As I was finishing that, someone named Jack Cowan came to the University of Chicago, who was developing and starting the Department of Theoretical Biology. It was then called the Committee on Mathematical Biology, I believe. And he started having seminars, and I started attending those seminars. I was fascinated by them. To do a postdoc, I asked my thesis advisor, Stuart Rice, for some suggestions of people who were doing biologically related work in England, because I didn't want to try to figure out how to talk another language. I ended up going to the University of Edinburgh, where there was just starting a department of machine intelligence and perception. There were three people. One was Christopher Longat-Higgins, who had been a chemistry professor in Cambridge. He had done quantum chemistry and was fascinated with music and the mind. And he was collaborating with someone named Richard Gregory, who did perception, and someone named Donald Mickey, who was a computer scientist. So they had just started that department, and I ended up getting a one-year postdoc from the National Institute of Health in Chicago. And I started doing research there related to visual perception and illusions. During my time there, I discovered an effect that you get when you superimpose one pattern of random dots on an exact copy of that pattern of random dots in a rotated position. Chris Longat-Higgins encouraged me to write up the article. He helped me write it up. It was eventually published in Nature. And that's an effect, a visual effect that's now called glass patterns. You get striking if you superimpose two images of exactly the same random dots in a slightly rotated position. You see, you get a very strong circular percept if the angle of rotation is not too big, a few degrees, 5 degrees or so. And I was fascinated by how the brain might be doing those sorts of computations that were necessary for the brain to perceive it as circles. And I was also delighted that I was able to publish the article. So I got something done in that 1 year in Scotland, in Edinburgh. And then during the course of that year, Jack Cowan sent me a note and said, would you be interested when you finish your year there to come back to Chicago and continue postdoctoral studies, probably working in visual perception and the neural networks, the brain, and so forth. And I took him up. I didn't have to look for that job, and I ended up going. So that was really the transformation from being a purely physical scientist to doing something related to biology, and was really the entree to working in biology to join the Committee on Mathematical Biology, or soon to be Department of Theoretical Biology in Chicago. So that's kind of the story of the transition, going from physical science into things related to biology.
Okay. And where does nonlinearity fit in the picture? Because a lot of your work is on nonlinear systems specifically.
Yeah.
Yes.
Yeah. So in Chicago, as a graduate student, I took standard courses in mathematical methods in physics, mathematical methods in chemistry. There was no nonlinear dynamics at all in any of those courses, as far as I remember. Even very basic concepts of stability and so forth, I don't remember ever learning about that in graduate school. But when I got to Chicago, instead of continuing work related to how neuroscience and visual perception, I met someone there by the name of Stuart Kaufman, who was working on mathematical models of genetic networks. So for people who know Stu and have heard him talk, he's extremely dynamic individual and has very, very fascinating ideas. One of the main thrusts of his research is that if you have some complex system, you can often get types of self-organization which lead to unexpected order. And Stuart is someone who had a medical degree and was, in fact, in Chicago, was even going and spending some time in emergency rooms, but really had a fascination with this basic concept of how does order arise in biology. The discovery that he made, which I found absolutely fascinating, was that if you take if you make a switching network, a Boolean switching network, some Boolean network was a Boolean network meant to represent genes. So each gene at any one step could be either 1 or 0. 1 meaning that it was being transcribed, 0 that it wasn't being transcribed. And then for each, he was taking large networks, let's say of 100 genes or 200 genes. And each gene had 2 other inputs in the original description, which were chosen randomly from other genes in the network. And each gene also realized a Boolean function on the states of 2 other genes. For example, the Boolean function could be an AND function. If both of the inputs were 1 at the previous time step, then the gene would be 1 at the next time step. So there are 16 different Boolean functions of 2 inputs, and each gene realized a randomly selected function out of those 16. And then what Stewart did is he started at some initial condition, which was chosen randomly. He had a network that was chosen randomly. And then he iterated to see what would happen at the next time step. So these Boolean networks, it's the basis of how modern computers work. There's a clock and there's a discrete time and there's sequential updating. And what Stewart discovered was instead of having exceedingly long cycles, he tended to have very short cycles of the order of 10 to 50 to 100 states, perhaps. And there tended to be very few of them. So why was that fascinating to me? In doing a degree in chemical physics, really related to statistical mechanics, theory of liquids, you tend to think of a phase space as being visited, the different states in the state space going from one to the next. So you say each state is going to be equally likely. There's something called Poincare recurrence time, which refers to how long, if you start at some state in this big phase space, how long does it take you to get back to that state? It tends to be, astronomically long for reasonably big systems. Well, in these model genetic networks, if there are 100 model genes, the state space is 2 to the 100th different states. And if you had some kind of random walking through those 100 states, you would never find your way back to the beginning, in any sort of reasonable time. The recurrence time would be huge. So it was rather amazing that the dynamics in the system tended to be very focused, very small number of final states, possible attractors, and very small cycle lengths. So I found that discovery very fascinating, but I had a problem. And the problem that I had is that there's in the body, in a real gene network in an organism, there's no discrete clock. There's no discrete clock like there is in a computer. So the natural way to start dealing with this was not to use the Boolean networks, but to then use differential equations in which genes could either be on or off, or they could also have a graded function. They could have some kind of sigmoidal function, which would be low or high with some intermediate states in between. And you could build, instead of having Boolean functions, you would have continuous functions, which were close to those Boolean functions. Or you could have functions that you might call step functions also. That would be another possibility. So what I started doing with Stewart is starting writing down differential equations where we put in continuous functions or step functions instead of the Boolean functions, and integrated the differential equations. Well, this is a very long answer to a short question, but those equations were nonlinear equations.
No, this is really interesting.
Huh?
No, please continue. This is really interesting.
Yeah. So to start dealing with those equations, you had to start thinking in terms of what's happening in a nonlinear equation. And so, the first thing that we looked at was looking at oscillations. So, in the Boolean switching networks, there were oscillations of those networks. And in the context of the differential equations, you can have oscillations, but the oscillations are now nonlinear oscillations. You have what people called a limit cycle. the limit cycle, if you start from some initial condition that's not on the oscillation, then you change, and asymptotically, as t goes to infinity, you approach that stable limit cycle. So that's a property that arises naturally in the context of differential equations. You also have the issue of stability. You can have a steady state, a fixed point, an equilibrium point, call it whatever you want, and then you can begin to analyze the stability of that state by doing mathematical operations, by linearizing the equations at that steady state. Those are techniques which are very basic techniques in nonlinear dynamics. There was nothing novel about those techniques, but they were completely unknown to me after having finished a PhD in chemistry at the University of Chicago in 1968, whenever it was. So that was how I got started, both doing work in nonlinear dynamics and also started doing models in biological systems.
Well, I have lots of questions. This is fascinating. And you mentioned a lot of the things that I wanted to ask. I think it's important you define for us and the audience some definitions, and we can build upon those definitions and ask some maybe little bit harder questions for the audience. But it would be good to explain what we mean, first of all, by nonlinear system and distinguish it from a linear one, and
Sure.
also perhaps explain what oscillations means for people that might not know. And let's start with these two.
Sure. So in the simplest case, if you have, first of all, what's a differential equation?
Yes.
So a differential equation is an equation that contains derivatives. What's a derivative? A derivative is an expression which is what's the rate of something as a function of something else. Typically, we're talking about the rate of change of a variable as a function of time. So a differential equation gives the rate of change of something as a function of time. And it's a function. So there's what's the rate of change of something as a function of time, and it's equal to something else. For example, if it's a constant, then you might have something just continuously increasing or continuously decreasing. If there's just one variable, so let's take one variable and say the rate of change of that is a function of time is just a constant, a positive constant, then it'll just increase at a constant rate. You could also say, what's the change of that? And you could say, supposing it's just proportional to what you have there. So the rate of change of something is proportional to the amount that's there. Let's say it's positive sign of proportionality, not negative. If it's a positive sign, you get what you call exponential growth.
Mm-hmm.
Okay, so it will just keep on increasing exponentially. So if I just have one variable, in a linear differential equation, the rate of change of something is just equal to the equation of a straight line on the right-hand side of the equation. So the rate of change is just equal to ax plus b. That's a linear equation.
Mm-hmm.
Dx dt is equal to ax plus b. It's a linear differential equation. If there's any other function on the right-hand side, which is not a straight line, then it's a nonlinear equation. For example, if it's proportional to the square of x, then it's a nonlinear equation. So that's the difference. And in higher dimensions, we have the rate of change not just of one variable, but of multiple variables. And on the right-hand side of the equation, in a linear equation, is just equations of straight lines or planes, or in higher dimensions, what you might call hyperplanes, ax plus by plus cz, for example.
Mhm.
But anything else on the right-hand side is a nonlinear equation. Okay, so that's the difference between linear equation. When in one of the examples of, now if we go to oscillations, one of the examples of oscillations that people are familiar with is a swing. So if you have a swing and uh, let's say it's just going back and forth a little bit, and say it's in an ideal situation, there's no friction at all. Once you start that swing going back and forth, it's just going to continue exactly at that same amplitude. You can make the amplitude a little bit bigger. It'll be more energetic. It'll go back and forth at a bigger amplitude. So that would be the equations for this ideal swing is a linear equation, and it can have oscillations. But what's the difference between this and a nonlinear system? So to me, the great example of a nonlinear oscillator in biology is the heart.
Mhm.
Uh, it continues beating. If we perturb it a little bit, and there are lots of ways of perturbing it a little bit, but keep keep the system basically the same, except giving it a little kick of some kind, it'll come back and it will beat with the same frequency it beat before, the same amplitude, and so forth. But with the swing, if you give it a little kick, a little change of its energy, then it'll keep on with that different energy, assuming that there's no friction. So in a nonlinear oscillator, you have what people would call a basin of attraction, a zone in which if you go off that basic oscillation, you'll come back to the same oscillation that you started out with. And this is a property that you can have in a nonlinear system, and you don't have it in a linear system. So those are just some basic notions about nonlinear oscillations. And also, if we have something like the heart, or with the cell cycle, or the menstrual cycle, for example, we're going to want to have an oscillation that's very, very stable. So it has to be a nonlinear oscillation, because those linear oscillations don't have the same stability properties.
I see. So how do you go about making a nonlinear system? And this might be a biological system, it might be something else. How do you identify the variables, and how do you gather information, and how do you start creating a mathematical model?
So, first of all, if you think about a biological experiment, you don't have to make a nonlinear system, because most of the biological systems, in my opinion, are nonlinear. It just happens naturally. So if you're going to do an experiment on the cardiac rhythm, for example,
Mhm.
you start off with cells that are beating,
Mhm.
or a whole animal, or part of an animal that's periodic. The the basic properties of that system are that it's a nonlinear system. So
Mhm.
from an experimental point of view, in doing work in biology, I don't think I think that it just happens naturally that you're going to be dealing with nonlinear systems.
Mhm.
From a mathematical point of view, uh, the approach that we've always taken is we try to extract and think about uh, simple ways that one can represent the basic properties of that system, and write down the equations for those simple ways to represent the properties of the system. And most of the time, you're going to end up with a nonlinear equation.
Mhm.
That's what happens with the equations for the genetic networks that I worked on with Stu Kaufman. Other people, a great applied mathematician named Balthasar van der Pol, was interested in electric circuits that could oscillate. And he made up an equation, which is a famous equation called the van der Pol oscillator, which is a nonlinear equation. It was useful for describing systems that he was interested in electrical engineering to construct oscillators. But it's always also very, very similar to equations that people have proposed as simplified models for nerve cells and cardiac cells. So the basic properties of the basic equations that you might start thinking about when you start thinking about what's actually happening in the real systems and how can we represent these in simple ways, then people end up naturally with nonlinear equations. Just to elaborate a teeny bit more, one of the great pieces of work that's been done in applications of mathematics to physiology were the Hodgkin-Huxley equations that were proposed back in 1952 to describe properties of squid giant
It's the
axolotls.
initiation of propagation of action potentials,
Yes,
right?
exactly. To action potentials and the ionic currents underlying those action potentials in squid giant axons. So beautiful work that was done in around 1950. Basic paper published in 1952 to describe the propagation of action potentials in nerve cells. Those equations are quite complicated. There are 4 different equations, I believe, and they're very nonlinear. They're very complicated. People tried to come up with a simplified version of those equations, and they did. They tried to get 2 different equations, dx dt and dy dt is equal to something on the right-hand side. And what turns out on the right-hand side is very similar to what van der Pol proposed way back in the 1930s. So those equations are called different things by different people, but
Fitzhugh,
Fitzhugh-Nagumo equation
yeah.
is a nonlinear equation which has properties which I would say, to me, are amazingly similar to the sorts of to the properties that you can see when you do experiments on nerve cells.
This is so interesting. So, how do you start? What's the first step? Let's say you want to study heart rhythms or cardiac arrhythmias or any other biological system. How do you start creating the mathematical model? How? What's the where do you start? Yeah.
So I think that different people start in different places, and I can say that what I've done is the best way to do it. It's different from what other people have done. For example, if you pose the question, supposing you want to make a model of a cardiac cell.
Mhm.
So one of the most important ways that people have done that is to follow along the steps of Hodgkin-Huxley. Hodgkin-Huxley, who we just mentioned,
Mhm.
formed equations and studied equations for propagation of action potentials in nerve cells. And people said, well, what are the different ion channels that are present in cardiac cells? And can we write down equations for those cardiac channels? Can we study the physiological properties of those ion channels and then study the properties of those ion channels and then develop an equation for that just the same as Hodgkin, using the same strategy as Hodgkin and Huxley. So a beautiful piece of work that did that was McAllister, Noble, and Chen, and I forget the exact year. So they developed an ionic model for cardiac cells. Naturally, the equations were nonlinear equations, but they're very complicated equations. You can look at the equations, even if you're expert in mathematics, and say, "Wow, this is very complicated. These are very complicated. We need a computer. We have to do computer simulations to get an idea of what's happening." So that's one approach, which has been a wildly successful approach. It's probably the approach that most people favor, but it's not the approach that we've tended to favor. So in the work that I've done and with collaborators, we have tried to develop models that were based and which was specifically oriented towards understanding properties of the physiological system that became manifest to us when we did experiments. So a lot of the modeling work that we've done has been strongly motivated by what we observe in experiments. And the experiments, I would also say, have been largely motivated by the nonlinear perspective that we have. So the nonlinear perspective, where we tend to look for qualitative features of dynamics and then try to understand how those qualitative features emerge. A qualitative feature, for example, can be, is there an oscillation or is there not an oscillation? Is there irregular dynamics? What's the nature of the transition from one dynamics to another dynamic? I can elaborate a little bit and say why this is natural in medicine. And if we're talking about the heart, there are rhythms in the heart which are called Wenke back rhythms. So in Wenke back rhythm, you tend to have very characteristic features, which are features that I would call qualitative features of the dynamics. So just to go back a little bit, in the heart, there's a pacemaker, which is called the sinus node. That's what beats regularly. It's a piece of muscle. It's part of muscle. It's not a nerve, but the frequency is modulated by nerve activity and circulating hormones and so forth. In a Wenke back rhythm, you can have the pacemaker beating a certain number of times, but the contraction of the heart can have a fewer number of times. So, for example, people talk about 4 to 3 Wenke back rhythms or 3 to 2 Wenke back rhythms. So 4 to 3 Wenke back rhythm means the pacemaker of the heart would beat 4 times, but the heart would only contract 3 times. The ventricles of the heart would only contract 3 times. Or if you have 3 to 2, then the pacemaker, the sinus node of the heart, would beat 3 times, but the ventricles would only contract 2 times. So these are arrhythmias. They've been known since the early 1900s, or perhaps a little bit before that. Amazingly enough, the original discoverer, or one of the early pioneers of that, this physician, Wenckebach, not sure how to pronounce it in German, actually developed mathematical models for that rhythm, which were nonlinear mathematical models. He didn't, I don't know if he knew any mathematics. I don't think he knew much mathematics, but he drew graphs. He represented the processes of the heart using graphs, and he studied what would happen. The graphs represented conduction of the heartbeat through the heart, through a region between the top chambers of the heart and the bottom chambers, called the region in between is called the atrioventricular node. He's studied graphical representation of the conduction time it takes to go through that region based on either experiments or I think on experimental observations he made in people's hearts, I believe. And he found that these different patterns would occur depending on how fast the sinus rate was. In other words, if the sinus rate was too fast, then you couldn't get this one-to-one conduction. You couldn't get each stimulus leading to a conduction through the heart. So you would get four driving beats and only 3 get through to the bottom of the heart, leading to a contraction. So the earliest physicians studying cardiac arrhythmias were really making up nonlinear models. And so you don't need to have differential equations representing all of the ion channels in the atrioventricular node and in the sinus node and the ventricles to come up and make those observations that as you change the frequency of stimulation in a real heart, you will observe these different sorts of rhythms. So this, that's kind of a bird's eye view of how you can go from the physiology to come up with a mathematical model, which is a nonlinear model, which can represent the dynamics of what's happening.
So you study graphs of how, let's say, the can you give us an example of a graph, for instance, when studying a biological system, and what's on the one axis, what's in the other one, and then what you do after that? So you have a graph, and then you study it, and how does that help you find to go to the next step?
Okay. So, here we're talking now instead of it's on the blackboard.
Yeah.
And, and in this conversation, we're talking about ideas which normally, if one was teaching it in a class, we'd now be 3/4 through one semester based on our conversation. Yeah. So, but we can keep on going because we'll see how intelligible it is. So so one of the experiments that we have focused on relates to early observations. So we mentioned the van der Pol equation, a nonlinear equation that gives stable oscillations, which in early paper that van der Pol wrote, he was showing how by hooking together these model equations, he could generate rhythms, which are similar to the rhythms that you get in the heart.
Mm-hmm.
And he also built electronic systems that had the same kind of rhythms. You can look back and find a paper by van der Pol and van der Mark from something like 1935, which gives an electronic model of winky back rhythms. You know, it's kind of amazing, but yeah, they were brilliant folks. In the work that I've been interested in, we've been fascinated by the kinds of rhythms you can get resulting from the coupling of two oscillators. Okay, or even more, taking the basic system in which you have one nonlinear oscillator, let's say the heart, and then you give periodic stimulation to that nonlinear system. So there were early mathematical studies that were done in which there were periodic stimuli given to the van der Pol equation, and early papers by mathematicians called Cartwright and Littlewood and Norman Levinson showed that you could have very complicated dynamics, including what people now call chaotic dynamics, happening when you have a nonlinear oscillator and you give periodic stimulation to it. So in the conversation here, we've skipped over these concepts of chaotic dynamics, but one of the fascinating discoveries that people made in the field of nonlinear dynamics is that you can have a deterministic system in which you observe irregular dynamics. Okay, so there are very simple examples of systems that can do that. Some of the simplest systems are what would be called iterative systems. In an iterative system, you have a rule, you start off at one place, you apply the rule, you get a new value, you apply the rule, you get a new value. The simplest example is compound interest. Every year you get 3% more than you got the first year, you keep on applying that and so forth. That would be a linear rule. But you could also have a nonlinear rule, whereas time goes on from one time, instead of getting a fixed ratio of what you had before, you have some more complicated function of what you had before. So you can get you can have a complicated rule. When people discovered that, or when it became widely known that some simple iterative systems could give rise to these complicated chaotic dynamics, aperiodic dynamics. In simple mathematical models, then I became fascinated with the concept that it might be possible to find chaotic dynamics in biological systems. Okay, so this is kind of around in the 1970s. There were beautiful papers by Robert May, Jim York, George Oster, other folks, in which they were demonstrating these very simple nonlinear iterative systems could give rise to chaotic dynamics. And it became a fascinating question to say, well, can we find this kind of chaotic dynamics in a biological system?
Mm-hmm.
And we also knew from the earlier work of mathematicians and engineers that periodically forced oscillators have the possibility of giving rise to chaotic dynamics. So in my own work and the development of my own work, a critical step for me in studying these problems was possible because in 1975, I started a faculty position at McGill University in Montreal. And I had kind of taken a wandering path from chemistry in Chicago to machine intelligent perception in Edinburgh to mathematical biology in Chicago. And then I also went to the Department of Physics and Astronomy in Rochester, finally finding a job, ending up at McGill University. And I had wanted to be in a place where I could have people who were doing experiments in physiological systems right down the hall from where I was sitting. And I was very fortunate. I was blessed by having a colleague named Alvin Schreier, who had been studying ionic properties of ion channels in little balls of beating heart cells from embryonic chicks. So amazing system in which these balls just beat periodically. And then I was also infinitely blessed by having met a fellow named Michael Guevara, who had had undergraduate degrees in physics and electrical engineering, and had also spent time working as an orderly in hospitals in Montreal, and knew about cardiac arrhythmias. And Michael Guevara wanted to do experiments related to cardiac arrhythmias. I had met him. At McGill University, another one of my fantastic colleagues was Michael Mackey. Michael Mackey and I gave a course, and Michael Guevara was a student in that course, and his solutions to our difficult problems we gave in that course were better than the solutions that we were able to come up with. So Michael Guevara said that he wanted to continue in doing a PhD in physiology. And he was interested in cardiac arrhythmias. And we teamed up with Michael Guevara and Alvin Schreier to be able to do experiments which were looking for chaotic dynamics in heart cells, in these periodically beating heart cells. And this is very long answer to question of
No, this is great. This is great. I can put the pieces together.
So we're about to say where the graph can come from. So one of the properties of nonlinear systems that are oscillating is that you can give a stimulus to the oscillation, and provided that stimulus doesn't destroy the oscillation or change it into something else, then after often a comparatively short period of time, the oscillation will be restored as before. So Alvin Schreier had a preparation in which he had these beating balls of cells. And he also was an expert in doing electrophysiology, an area where you have these beating balls of cells and then you can inject electric currents in various ways. And Michael Guevara had a strong background in electrical engineering and physics and was interested in cardiac arrhythmias. So if you have the beating ball of cells now, you can give a little shock to it, just quite a short shock. That will perturb the rhythm, but the original rhythm will be reset very quickly generally, but it will now be beating at a different time than it would have been beating if you had not given the shock. Okay, so you give a shock, and instead of it beating at this time, it's going to beat a little earlier or a little later. I don't know which side is earlier or later. Okay? Well, you can measure that. It's very easy to measure that. You can give a shock at different phases of the cycle.
Mm-hmm.
And to each of those shocks at different phases of the cycle, you can measure the timing of the beat, whether it's going to be earlier or later. And you can then draw a graph, which is, what's that change in time as a function of the phase in the cycle at which you give the stimulus. So there's the graph. That's one of the basic graphs that you can do. And that's a graph that you measure. You don't have to know any mathematics to do that. It's just an experimental measurement. So then there's a conceptual step, which is that, and you can almost imagine that without writing down any equations, which is here I have an oscillation that's going around. I give a shock at a certain point in the oscillation. It's now going to reset the timing when the next beat is going to occur, when the next action potential will occur. And I've now measured that. So I know where that next beat is coming. But now I'm going to give another shock, maybe before that beat comes, maybe after that beat comes. And this is also going to, since I've come back now and reestablished the rhythm, let's say it's reestablished very quickly before the next shock arrives, I can now know the effect of the next shock. So once I give one shock, I change the timing of the rhythm. I know what that change in timing is going to be. Then I give another shock. That changes the timing of the rhythm. And because I've now measured in a completely separate experiment the effect of those shocks at different phases, at different times in the rhythm, I know mathematically what that is. And I can do this process once again of iteration in order to determine what the effect of this periodic chain of shocks is going to be. So in effect, in this in developing the system, one has a system which is very, very similar to the very simple nonlinear equations, nonlinear iterative systems that were being studied by May and York and others. And I can do two things. Number one is I can do the experiment. I can give shocks at different frequencies or using any sequence, in fact, but different frequencies, and I can see what's happening. And you don't have to be a great experiment. To get everything to work, especially back in the late 1970s and 80s, was major experimental work done by Alvin Schreier and Michael Guevara to get everything to work. But to see what the rhythm is, you can just count. Here's the number of pulses. Here's the number of action potentials, and you can just look and you can see what's observed. You don't have to be a mathematician to look and see what's observed. And in fact, this is exactly the same sort of thing that Wenckebach had been doing in the 1930s, or the early cardiac electrophysiologists, cardiologists were counting, looking at the number of sinus beats and the number of ventricular beats. So this is exactly doing the same thing, looking and seeing the number of stimuli, the number of action potentials, and also doing this in a very systematic fashion, very, very carefully, to try to see if there are any combinations of amplitude of stimulus and frequency of stimulus, which might give some irregular rhythms. And in fact, through this very meticulous and careful analysis, Michael Guevara came up with some sets of frequencies and amplitudes that gave irregular dynamics. And in one sense, that could have been done without knowing any mathematics at all. That's just an experiment. You stimulated one frequency, you see what happens. But in order to interpret that, we now have the experimental measurement of the phase resetting. And with the experimental measurement of the phase resetting curve, you could do the iterations and say, at certain stimulation frequencies, you might see some regular rhythms. Let's say one stimulus to one action potential, or regular rhythms in which you have 4 stimuli to 3 action potentials. But at other frequencies, you get these rather complicated rhythms in which you don't get quickly repeating patterns. And those were happening at about the same frequencies that we were observing these chaotic dynamics in the mathematical model, in which we had, which was based on iteration of the experimentally measured phase resetting curves. So to us, this was a very exciting advance, and it is just doing graphical iteration of experimentally measured functions. Of course, to do that, generally, we take equations and we fit those equations to those functions. So we can do this without just doing it completely graphically. We can have an analytic mathematical expression for those functions.
This makes more sense now. I want to ask you about education. I will come back to specific things about your work, class patterns, and visual perception. But I always like to understand, when talking to professors and experts like yourself, well, how do you learn, and how do you view the education system today, from high school to university? And do you is there ways you think that it could be better?
So, yeah. So it, that's a great question, and I wish I had great answers for it. I don't know that I have great answers. I don't have intimate knowledge with what happens in high school and grade school, except I did have children who went to high school and grade school and university and have careers which are, related to science in terms of things. And so they've learned very well. In my education, and this is something to me that's very interesting. In my education, I went to public schools and public universities. So all of my education from elementary school, high school, and college was using the public school system in the United States, New York City and the United States, because my family didn't have any money. We didn't have money for private schools. My parents had been public school teachers. And I think I got quite a good education. I think one of the things that I think was crucial in my early education was in high school, where I was in something called the math team class. So in the math team class, there were people who there were competitions where 4 or 5 of the top students in the school would compete against the 4 or 5 top students in other schools. And they were just like doing basketball or something else, but it would be math problems. And I was not one of the top 4 or 5 people, but I was in the class of the 30 people who were in the math team class. And one of the things in that class is that they gave us hard problems, which challenged us at a time in our lives where I think it's very important to be challenged. So that's kind of in the early teenage years. We were given problems. And one problem I remember, I mean, this is out of the way, but if anybody is listening to this, I'm not sure that people listen to these things, but if somebody listens to this and likes geometry, here's one of the problems I remember from high school, which is that if you have, I think the problem was if you have 2 angle bisectors of a triangle are equal in length, to prove the triangle is isosceles. Okay? 2 angles, the angle bisector of 2 of those angles are equal in length, to prove the triangle is isosceles. That's a very hard problem. And that's the kind of problem that we were given at an early stage. So I love doing those things. It's part of the education. So the only thing that I know about in the earlier, during these formative years is I think it's important to really challenge people with hard problems. And I don't know that my children or now my grandchildren were given challenging problems of that sort as part of the educational system. I don't know where it is where you went to school, but to me that's something which I think was unbelievably important in terms of just my own development. At the university where I taught for many years, and in medical school, the question of education and education in mathematics and so forth is something which I've thought about, and I've had my opinion, and I'm not sure that my opinion is correct. But I taught a course for many years, which was directed towards biology students who had taken a year of calculus, who had taken a year of calculus, but nothing more. And I wanted to teach them the basics of nonlinear dynamics in one semester. And I taught a course such as that. And I wrote a book with Daniel Kaplan called Understanding Nonlinear Dynamics, and which was really based on that course, in which I think we do exactly that. We go from somebody who knows some basic knowledge of calculus, to be able to expose them to the basic concepts of nonlinear dynamics in terms of iterative systems like we've talked about, chaotic dynamics, stability of simple differential equations, and so forth. It's totally different from the way I was taught when I went to college and graduate school. And unfortunately, I think it's totally different from the way people teach mathematics now. I think there's a big tendency in teaching, for example, this is kind of getting into the weeds, but in the second semester of calculus, people learn a lot of tricks for doing integrals. But nobody has to know that. Maybe 75 years ago, before computers, engineers had to know how to do integrals, but people don't necessarily have to know integrals now. When people do differential equations, when the people take a course in differential equation, they learn tricks for integrating differential equations, but the qualitative geometric theory of differential equations is still not very prominent in the elementary courses given in mathematics. And to me, someone who was never necessarily very strong in being able to do analytical integrations or computations, I think that the qualitative approach is something that could be taught and should be taught even at a basic stage. I think that in undergraduates, I think that basic education, which gives a course similar to the course that I taught and is still being taught at McGill University in Montreal, and probably in a few other places, is something which could be part of the curriculum, but is actually not part of the curriculum in many places. So courses like that, I think, are still not being taught much. If you go to medical school, if you go past college, so you're in medical school now, and I've done sabbaticals a few times with medical doctors. I've had collaborations, and I've gone and spent time going to lectures from a cardiologist named Ari Goldberger, who has done prominent work related to cardiac arrhythmias and fluctuations in normal cardiac rhythms. And I've also spent time with a cardiologist named Mark Josephson, who is really one of the giants in cardiac electrophysiology, who unfortunately died prematurely several years ago. During one of the times I went to visit, so Mark Josephson at that time was at the Beth Israel Deaconess Hospital in Boston. It's one of the teaching hospitals associated with Harvard University. And I had decided that it was important to try to teach the people who were studying to be cardiologists what a nonlinear equation was, what a limit cycle was, how we could look at some of these basic properties of resetting cardiac rhythms and seeing what happens. So I worked out kind of 5-hour lectures or something like that, which I was going to present to Mark Josephson's group. Of course, I thought, okay, they're cardiologists. They don't have the slightest idea what a limit cycle is. How hard is a limit cycle? How can that be possible? They have to know this. I have to teach them that. So I think I gave one of the 5 lectures. And I think that what I learned from doing that is that in order to do what they were doing, they didn't have to know any of the mathematics.
Mhm.
So that was a great disappointment and shock to me. Uh, the cardiologists who were doing procedures of incredible sophistication now, dealing with this nonlinear oscillator called the heart, do not have to know what a differential equation is. They do not have to know what a limit cycle oscillation is. They can do it all uh, based on uh, just the basic training of mathematics. Would there, would they be able to do better if they knew what a nonlinear differential equation is? I actually doubt that they could. Are some of them fascinated by the mathematical aspects? Yes, a few of them, but most of the people don't have training in mathematics or necessarily even the interest in the mathematics to do it. I think that in cardiology, you find a number of the cardiologists who go into these areas of electrophysiology are attracted to that because it has a more naturally mathematical electrical engineering. So I think that you have several people in cardiac electrophysiology who have quite a strong background in either engineering or physics or mathematics. But for
Mhm.
them to do their work, they then don't necessarily have to know any of the mathematics.
What motivated you through your career to study these things? Is it helping people? Is it curiosity? Is it a combination of things?
So, yeah, my career has been driven more by curiosity than saying I really want to help people. It's very
Mhm.
selfish,
Mhm.
but uh, but you know, the work that I've done and the work with colleagues has been really motivated by basic science rather rather than practical applications. We would love to have practical applications, and there was one problem that we worked at which has had strong practical applications, which it relates to developing algorithms for detection of atrial fibrillation, uh, a cardiac arrhythmia based on the based on the recordings of the electrocardiogram. So that has had implications, and now everybody's devices, their watches, their Oura rings, their Apple watches are able to uh, come up and detect atrial fibrillation. Exactly what algorithm is used in various devices is not clear, but our algorithm was implemented in a device that was sold by Medtronic, who licensed the work from McGill University. So that's one practical application, which has been important. In work we've been doing now and going back many years, also very interested in practical applications related to factors that may predispose towards sudden cardiac death based on analysis of arrhythmias that people have called premature ventricular complexes or contractions. So these are practical applications that we've been interested in, but the driving force in this has been the basic science questions and curiosity.
Mhm. I That makes sense. And curiosity is it's something that I don't always see when it comes to my peers, and it's almost sometimes it feels like it's such a it's such a strong factor that produces really good productive work. People being curious, really trying to question and understand things, and and we kind of forget that sometimes. Um, I feel like the most productive when I'm sitting down and I'm just really curious about the topic and I'm asking more questions and I'm learning about it more. And yeah, I think it's sometimes forgotten within education, and how to cultivate students who have curiosity, because that can lead to a more productive outcome. Having said that, by the way, how are you feeling? Are you tired? Can I continue? Shall I continue?
I can keep up for a
Oh,
while.
okay, good.
Yeah.
Awesome.
It's
So,
fun.
um, I'm a little bit confused when it comes to,
But
um,
let
yeah,
me just ask you something about the curiosity in
yeah,
medicine and make a comment, which is that the training of medical doctors is very different than the training of people in basic science. So if I go to a doctor, I don't want a PhD thesis on what the mechanism is of my premature ventricular complexes.
hmm
I want them to tell me, do I have to do anything about this? Is it serious? Is it not serious? And they don't have to know anything about the mathematics to do that. They, but they do have to know, okay, with people who have had this kind of situation previously, uh, if I do nothing, do they die sooner? Do they get sicker? If I do something, sometimes you do something and they die sooner or get sicker from what you do.
hmm
And so that's what the training in medicine is. So that's what you're training now to,
hmm
to be a medical doctor, right?
hmm
So, so that's what the training has to be focused on. So my notion that all cardiologists should know what a nonlinear oscillator is, I no longer think that that's really true. Like
hmm
they have to know what to do.
For sure. Yes, I agree. I think also, though, it can bring a lot of innovation if students, not necessarily undergraduates, but in general, have the core curriculum that they need to know to do their job, but also are free to have some time to perhaps go into maybe even niche areas that they might find interest in. Um, and yeah, I don't, for instance, the most productive, well, when I say maybe productive isn't the right word, but some of the most interesting times I've had at universities when they give us a project and they leave it open enough so we can just find a path that we might find interesting. So, for instance, this was my favorite was they said to us do a project presentation, but the topic is just so it has to be science related. And so and so I did a chaos theory in medicine, and I just talked a little bit about Hatin Huxley and Fitzhugh Nagumo, and I just found it really, really interesting. And definitely, this by itself, if you just study random things you find interesting, yeah, it's not going to make the a medical doctor necessarily that knows the core things that's they're going to face in everyday life as a doctor. But I think in as a as an extracurricular thing, I think it seems to have some benefit in keeping a spark alive inside the student.
So can I tell you one of kind of an interesting anecdote
Mhm.
about curiosity in mathematics and cardiology? So we discovered that one of the mechanisms for generating these extra heartbeats, these premature ventricular complexes, arises just from the property of two independent oscillators going along at their own frequency. Okay, so that's a mechanism. One of the oscillators is the sinus node oscillation at its own frequency. And then you can have another pacemaker in the ventricles, which is beating with it another different frequency.
Mhm.
Well, those are just two basic assumptions, two oscillations at their own frequencies. And then there are also refractory times. After one of them beats, there's a time when the other one can't beat. You know, you can recognize that this is very similar to the experiments I described earlier, where we're stimulating these chick heart cells with one frequency and seeing what rhythm arises. But in this situation, it's even simpler. You have the two oscillations and they're not resetting each other. They
Mhm.
just, and there are amazing properties of that mechanism.
Mhm.
I won't have to say exactly what the properties are, but they're kind of unbelievable. And not only that, you can find electrocardiograms in classic textbooks in electrocardiography, in these atlases of electrocardiograms, in which you can see these properties happening. The properties relate to the number of normal beats, the number of sinus beats between two abnormal beats.
Mhm.
There are restrictions on the numbers you can see between those. So when we discovered this result, we 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 thought it was amazing. You know, it's like a basic something in number theory, which is not very well known, but which is happening in some people, 100%,
Mhm.
absolutely. The basic mechanism had been described by cardiologists going back again 120 years or whatever from now. When I gave a talk about that
Mhm.
in one of the leading cardiology and electrocardiology departments, I won't say where, and I won't tell the name of the person, the head of the department, who was a very distinguished cardiac electrocardiologist, after I described the result, he got very angry. And he said, this is nothing more than mental masturbation.
Mhm.
Because it was this incredible result related to number theory about cardiac electrocardiograms. I thought it was incredible because here's something that's really happening. And he thought it was mental masturbation because it wasn't directly applicable to anything that he would do.
Mhm.
Now, in subsequent years, when I've bumped into the same person at meetings, he has often apologized profusely and said,
Mhm.
well, that wasn't very nice of me to say that or something like that. But it to me, it kind of epitomizes the dichotomy between the basic science approach, which is to find out amazing things about the real world, and the cardiology approach, which is to know something which is able to help people.
Mhm.
Anyway,
Well, that's interesting.
the notion of what role should curiosity and basic science play in the education of of people, and particularly, you're now undergoing a medical degree.
Mm-hmm.
So you have an enormous amount of material that you have to learn and
Mm-hmm.
you have to master to some level. And the people who, in some sense, self-select to take that path in life are not necessarily the same people who, really have the drive to do things related to the basic science questions.
Interesting. Um, yeah. Um, it almost feels like, though, they are interconnected sometimes, because sometimes, for instance, uh, let's say something in philosophy like the trolley problem, uh, where you sit down and think about who do you sacrifice. You have five people in one rail track, and in the other train track you have one person, and maybe that one person is your mom, or maybe that one person has 40 years to live and the other five people have 1 year to live each. And so then I sometimes get accused by my friends that, oh yeah, because I like philosophy, I occasionally bring philosophers on the podcast. So I have Dr. Barrett on consciousness and panpsychism on Tuesday, which I'm really excited about. Um, and they tell me, well, this doesn't really have much practical application, but it does. For instance, now with automatic cars, and it's not something you'd expect, but it came out of nowhere from someone that's been theorizing something in the past. Suddenly, you have a car that realizes, oh, there's a car crash about to happen now.
Mhm.
And if I steer the wheel left, there's going to be a poor old person hit by the vehicle. But if I steer it right or continue going forwards, there's going to be another group of people, and suddenly these ethics become practical ethics. And so sometimes it also, I don't know, but maybe by this logic, something similar might happen when it comes to this theory that might seem very abstract to someone that's just focused on the practical application, but then somehow some connection happens. I'm not saying this always happens, but I think this is something that might happen.
Yeah. So, you know, uh, I think, so first of all, in cardiology and cardiac electrophysiology, which is, I'm not a medical doctor, but that's the branch of medicine I know most about.
Mhm.
There are fantastic technologies now for mapping what happens inside the heart, for being able to do what's called ablations to destroy part of cardiac tissue, which may be involved in potentially fatal mechanisms for arrhythmias. Um, in many of the circumstances, the arrhythmias are generated, the dangerous arrhythmias are generated by what's called a reentrant mechanism.
Okay.
On a reentrant mechanism, the pace of the rhythm is not set by the pacemaker of the heart, but by the time it takes an excitation to go around some circuitous route. And one of the ways this reentry can occur is there can be spiral waves of circulation inside the heart. One of the people who was a basic scientist who helped establish that concept of a circulating wave is someone who was a close friend and colleague named Art Winfrey, who demonstrated initially in chemical systems that you could have these circulating waves of spiral waves. And then he did some mathematical simulations in which he showed these kinds of circulating waves and spiral waves. And there were a couple of early experiments that also showed these kinds of waves, some by a fellow named Alessi in the Netherlands. But this was not mainstream going back into the 1970s and 80s, when Art Winfrey was proposing this, and who also wrote an article called something like Sudden Death, a Problem in Topology in the Scientific American. But now, all cardiologists very much accept the notion of these spiral waves of activity. You can see basic papers, or you can see in clinical medical textbooks, you can have pictures of that, like schematic pictures of circulating waves and so forth. The concepts, they're not 100% original with Winfrey. There were earlier papers that came before him, some which kind of hinted at this, but his work really was fundamental in establishing these kinds of waves, and also demonstrating them in different kinds of cardiac preparations, both in vitro and in vivo. So it's one example where the earlier very much curiosity-driven work, very much outside the range of cardiology, has turned out to be something where is now very much accepted by cardiologists and the medical doctors, and probably many of them couldn't really trace back this history to recognize fundamental role that Art Winfrey played in establishing this. So they're interesting examples, but the real advances that have happened in cardiology that make ablations possible and so forth came about not from the contributions of people who know nonlinear dynamics, but the contributions of engineers working with cardiologists to develop these very, very powerful technologies. And the very powerful technologies do not necessarily, or I shouldn't say not necessarily, I would say not at all, require the inputs of people with knowledge in nonlinear dynamics.
Interesting. I wanted to ask you about how do we distinguish deterministic chaos from randomness? Because when something looks random, how do we decide if it's truly random or if it's just very, very complex and we can't figure it out?
Okay, so okay, first, so this is an area where I might be called what people in this sense called a strict constructionist, that I have a very precise notion of what the term chaos from a mathematical context means, and as opposed to a natural language meaning of the term chaos. So to me, if something is chaotic, it means that there's a underlying deterministic system. It's aperiodic. It's sensitive to initial conditions, meaning meaning that two initial conditions close to each other will diverge. And it's bounded. Things have to stay in a finite volume. They don't go off to infinity. That definition precludes observation of chaos in the real world, because in the real world, there's always going to be some kind of noise, stochastic process, which we're not going to be able to control. So when we wrote our early paper, which I described earlier about irregular dynamics in the periodically stimulated chicken heart cells, we were demonstrating, our interpretation of that is that this is an example of chaotic dynamics in a deterministic, in a biological system. But my colleague, the person who was doing the experiments, Michael Cavera, said we can't call it chaotic dynamics because there are stochastic things. He insisted that our title could not be chaotic dynamics. It had to be irregular dynamics because it was irregular.
Mhm.
But since it was in a real system in which we knew there was noise, we couldn't call it chaotic dynamics. Whereas at the same time, many other people were writing papers about chaotic dynamics in different kinds of physical systems. And so from a very strict sense, in a real system, you can have noise playing a role. So in some sense, but do I think that what we were seeing is really chaotic dynamics? The answer is yes. I think that. And the reason is because we had a system that was reasonably well described, and it's not 100% described. We can, if you say, what are the defects in the model you had, I can tell you.
Mhm.
But we were seeing irregular dynamics at frequencies and amplitudes in which a mathematical model that gave pretty good agreement with the experiments over a range of frequencies and amplitudes was showing chaotic dynamics. So that may be as well as you can do to say chaotic dynamics. Now, what you're really asking in your question, though, is there are lots of systems. So one of the answers is, well, you never really have chaotic dynamics in natural systems because there's always noise. And the definition of chaos necessarily says that you have a deterministic system. So, okay, but that's maybe too pedantic. But, particularly going back 40 years, people were writing papers in which they said there's chaotic dynamics here and the chaotic dynamics there. And there are a variety of tests which people were proposing were important. And I think that there were basic logical errors that people were making.
Mhm.
One of the logical errors is there's something called the Lyapunov exponent. Lyapunov exponent measures divergence of neighboring trajectories related to sensitive dependence on initial conditions. In natural systems, you can develop algorithms, and people developed algorithms to try to measure the divergence of these trajectories. And those algorithms, if applied carefully by people who knew what they were doing in differential equations and mathematical models of chaotic systems, could be used to give a good measure associated with chaotic dynamics. So that's one of the parts of the definition, that you have divergence of neighboring trajectories. It can be measured by a Lyapunov exponent. A property of chaotic dynamics
Mhm.
is that you have this divergence of orbits, okay? But if you develop an algorithm to apply this in an experimental system, you may measure a positive Lyapunov number. You measure something that says that there's divergence of neighboring trajectories, but you're now doing something in a system that has noise in it and can have fluctuations, which can lead to this being positive, to identifying chaos in a system which is simply noisy. And this is something that happened time and time again. At a very early stage, I took data from these cardiac beating chick hearts that were very regular. Very regular in period means that there's a fluctuation of maybe 2 or 3% in the period from one beat to the next. And I went down to one of the places that had developed an algorithm for identification of chaos via the Lyapunov exponent in Harry Swinney's laboratory in Texas, the Wolf-Swinney. Well, there's something called Wolf-Swinney. I think there may be some other co-authors there. And we took the data, and that from my perspective of what's happening there, here we had a periodic oscillation with slight fluctuations in the period and so forth. But when you tried to apply the algorithm that was developed, it would always give that this was chaotic dynamics, that it had a positive Lyapunov exponent, which was one of the characteristics of chaos. So there were many papers published in those days which would say, well, we have a positive Lyapunov exponent, maybe some other measures similarly, which would be, fractional dimension or whatever you want to talk about, which would agree with what you see there. But it doesn't necessarily mean that this is what you would call deterministic chaos, if you thought about it very carefully, in my personal opinion. And I think that was a problem. The other thing that you raise is, here are things which are very complicated, and may they not really, are they chaotic, or can they just be very complicated? And I think that I think that a lot of the things in the real world can be very complicated, but they're not necessarily, they're not identified with a low-dimensional dynamical system that has deterministic chaos. So to my mind, if you want to talk specifically about this concept of chaos, I think it's the criteria that I have is that you want to have a mathematical model that is believable, that can show both regular and irregular dynamics as you change parameters, and you want to show agreement. It has regular dynamics over some range of parameters, irregular dynamics experimentally in another range of parameters, and in the mathematical model, you can demonstrate that there's chaotic dynamics in the mathematical model in the same values, same places where you see chaotic dynamics. The irregular chaotic dynamics in the mathematical model, simple low-dimensional mathematical model, and irregular dynamics in the experiments. And I'd say that there are several well-done experiments, including experiments, for example, by people like Harry Swinney, in which these kind of criteria applied. There are other things. Is the sequence of changes of dynamics or bifurcations similar in the experimental system and in the mathematical equations? So that could also be something that would lead us to believe that something was associated with chaos. But the issue of irregular dynamics in higher dimensional systems, I think there's an area that I don't know is very well understood, because one of the things that I've been interested in also are these equations of genetic networks that I mentioned at the beginning of the of the of our conversation here. And as you increase the number of these elements, number of these model genes, and the number of inputs, you can go into range in which we know we have deterministic equations. And it appears to be irregular, but you're also having behavior that's like these wandering in these ergodic systems where you go all over phase space. In some of the lower dimensional equations of those models, let's say in 4 dimensions, we have good enough control over equations so that we can say, this is really deterministic chaos in these equations, because we can reduce it to a low dimensional system that we can analyze. But we can also take this same type of equations and now go up into 50 dimensions and integrate the equations, and we get very irregular dynamics. And we know the system is deterministic. We know it's not periodic. We don't necessarily know if there might be some behavior which will repeat eventually. And I think that a lot of real systems, that might be some kind of picture of what might be happening, that you can be in a deterministic system, which now becomes like the systems we look at in statistical physics, where you have ergodicity and things like that. But I think that those ranges, if you look at systems in, let's say, 10 to 30 dimensions, deterministic systems in 10 to 30 dimensions, with chaotic dynamics, I think that there's a whole area there that's not necessarily well understood.
Interesting. I'm just going to ask you a couple questions about your work specifically, and then we'll go and do a nice, more relaxed. The last section is just a couple more relaxed questions
Oh, okay.
outside. But when it comes to your work, what's the work that you're most proud of, that you enjoyed the most? I'm aware of you mentioned already class patterns and your work with cardiac arrhythmias, and I would like to learn a little bit more about those two specifically, but also things that you personally found that these are the things I'm most proud of.
So, it's a tough question, because I tend to like, when I do work almost all of the time, I tend to like what we've eventually done. I was talking to a colleague yesterday who studies respiration, and I was mentioning early work we did in respiration, and I was pointing out things, and I said, there's really good paper that we did, and then, some other papers, there's really, so it's like children. You don't really want to say one thing
I see.
is really a lot. A lot of some of the things that I think are quite interesting, and nobody actually cares about except me. I find things, some of the work that we've done, I think is fascinating, and absolutely nobody really cites it or cares about it or whatever. I think that the work that was really, in some sense, the biggest challenge and came at a very early stage was the work I described in detail earlier about the periodic stimulation of the Chick-Hartzell
Mm,
aggregates. I think that the combination of experimental prowess, which is completely due to my colleagues Alvin Troyer and Michael Guevara,
mm,
combined with the mathematical insights that were necessary to interpret that, was one of the things that came at a very early stage in the development of that area. And I think that that's an example of a very, you know, quite interesting work. I also collaborated with Michael Mackey uh, on time delay equations, models for disease. And one of the equations that we presented in that, which was written down by Mike Mackey, has become well known as the Mackey-Glass equations. It was deterministic equation with time delay that shows chaotic dynamics, and we studied that. So that's another one of the things that we did that was very influential, and I'm delighted to have played a role in development of that.
mhm. What can you explain to me a little bit class patterns? Because you mentioned it in the beginning, and I was aware of the term before our podcast, but I
Yeah.
don't really understand it.
So just to repeat, you you can you can take a random pattern of dots.
Mm,
Uh, what? Well, let me. I can just. I'll diverge a little bit just to say how it was discovered. So when
mm,
I was at the University of Edinburgh on the
mm,
Department of Machine Intelligence and Perception,
mhm,
the professor who was my supervisor and mentor, Christopher Longat-Higgins, took a trip to the University of Rochester in Syracuse, in Rochester. Wait, no, not the University of Rochester, to Syracuse University,
okay.
where there was a physicist named Eric Harth. And Harth had an experiment that he showed him, which was based on the copier machines, the Xerox machines that we had at those days, in which you take a blank piece of paper and you take a copy of that, and then you take the copy and you make a copy of that, and then you take a copy. So you keep on taking the copy and taking a copy of the copy of the copy of the copy, keeping on iterating that. And after you've done that about 10 or 15 times, you end up with a pattern of dots. And the pattern of dots looks irregular. So Christopher Longat-Higgins came and he showed the people working in his laboratory this experiment. And it was a fascinating experiment. The reason that it happens is slight imperfections or dust on the copier or little brown specks in the paper kind of get copied and then continue to be copied as you keep on doing this, and you eventually build up these patterns of dots. The dots don't keep on growing because in these early Xerox machines, there were local inhibitory fields. There was electrostatic interactions. And so you couldn't get dots bigger than a certain size. If you took something completely black and tried to do a copy of it, you'd get the edges of it rather than the thing you were trying to copy. There were processes that people can call lateral inhibition. And processes of lateral inhibition are important in vision, they're important in development and other areas. I, just having done a PhD in chemical physics, was interested in the spatial pattern of dots. And I was interested in trying to compute what's called the spatial autocorrelation function of the dots, which is if you know that you have a dot at one point in space, what's the probability that you find another dot at some distance away from it? So that's called an autocorrelation function.
Mm-hmm.
And I wanted to measure that in the pattern of dots by here's dots on a piece of paper, black on white. I made a transparency of that by taking a copy of that. You could take the copy of that on a Xerox machine on a transparent piece of plastic. And in the process of doing that, I had the initial pattern of dots. I had a second pattern of dots, which was on top of it. If they're superimposed exactly, you just see the pattern of dots. But if you just rotate one slightly with respect to the other, then you start seeing circular patterns. They're very striking. And so just in the process of trying to compute the spatial to measure the spatial autocorrelation function, I would take the transparency. What I was doing with that, I took the transparency and I tried to shine it up on the wall. And on the wall, I had a bullseye pattern. So I could put a single dot at the center of the bullseye and count the number of dots in each of the rings around that central dot. So I was trying to use the transparency to project it on the bullseye pattern and do this for different dots, put different dots in the center and measure. So that was my idea of what to do. And I happened to have a shift. You naturally do this and you see these very striking patterns that arose, and I showed them to my mentor, my supervisor, Longat Higgins, and he said, "Wow, that's terrific. You have to write that up." And I said, "Really?" And so, yeah, so we wrote it up, looked up some of the basic physiology that people were just studying about the properties of the visual cortex and how the visual cortex might be detecting these kinds of correlations, what kind of computation could be done. And with the assistance of Longat Higgins, wrote up an initial paper. Longat Higgins, when I did the draft and put his name on it as a senior author, he said, no, this is your work. You should just be the author, with great generosity, for which I will always be grateful.
That's very nice.
But that, so this, so I think that Longat Higgins, who is unfortunately has been deceased for a while now, was really a brilliant and very, very wise and generous man. And that, having done that, that was the one thing I got done in the year in Edinburgh.
Mm-hmm.
But it partially gave the confidence to continue and do the switch from statistical mechanics and theory of liquids and chemical physics into interdisciplinary areas, which were not very popular in those days.
Interesting. Is there anything that you'd like to talk about that we haven't covered?
Oh, we've covered lots of ground. I didn't have a list of things I wanted to cover. Was there anything that you had on the list that you wanted to mention?
A lot of the stuff I wanted to talk about, we've talked. I just want to ask you some more kind of everyday life questions that I also find really interesting when talking to guests, just because I think when it comes to understanding people that are innovative and are experts in different fields, I think it's worth understanding also, well, what do you guys do to relax? What do you do outside of work? Is there anything in particular that you find makes your head clearer and more productive?
Oh, I don't know that I can say my head is ever clear or productive, but uh, one of the things, one of my hobbies has been playing the French horn.
Mm-hmm.
A French horn is this crazy instrument that has 13 feet of tubing and a mouthpiece.
Mm-hmm.
Oh, I always loved the sound of the French horn,
Mm-hmm.
and I think I started playing it in a music camp, a summer music camp, when I was 12 or 13 or something. I forget exactly the age. And I played it in high school and college. And
Mm-hmm.
then in graduate school, I was in the University of Chicago Symphony Orchestra playing the fourth horn part. I was never very good, but I played in some wonderful pieces of music like Mahler's First Symphony and Bruckner's Fourth Symphony. But um, back in those days, we lived in Chicago, which was a tough city, and the person who played the first horn had his French horn stolen.
Okay.
And I said, okay, well, you can borrow my horn. And then my horn was stolen. And I thought, okay, this is God telling me that I really don't have to, you know, time to stop playing. I got my PhD, left Chicago, no more French horn. So for many years, I didn't play the horn at all. And then when I finally arrived at McGill University, I ended up buying a used horn, a very cheap used horn, and started playing it again. And then was played in amateur orchestras really until a couple of years ago, and even played in a concert last year. So in terms of hobbies, that's one hobby which which was very rewarding, which I love doing. Uh,
Mm-hmm.
another hobby that I've done is hiking.
Mm.
So I've also greatly enjoyed doing hiking in outside. Like, yeah, of course. I was never one of the best athletes when I was in elementary school and high school and college. I was always would be the last one to be chosen on the team, but I very much enjoy hiking and getting outside, and now also it's something that I continue to do with great pleasure.
It seems that people, um, when it comes to creative things, be it music or making paintings or something like that, and also when it comes to things that have to do with um, exposure to nature, may it be swimming or hiking, it seems these things are a common pattern when it comes to things that people enjoy and make them relax and make them more productive. Um, how was your time on the podcast? Did you enjoy it?
Yeah, greatly.
I'm glad.
Thank you.
I really enjoy doing these conversations too. Just gonna ask you two more questions. The last one I ask it to everyone. So I'm always curious to see what people have to say. Um, and so if people that are listening forgot everything that we talked about, what's one key takeaway that you'd like them to take home?
Um, I mean, there are I would say two things for me that have been really important. One is the curiosity, which we mentioned before, that to follow what you're curious about. Don't care whether you can get a big grant by doing it or whatever. Follow your curiosity. And the second thing is the importance of being tenacious. So, especially as a basic scientist, there are going to be lots of times when people don't really care about what you're doing or are going to not give you a job, not offer you a job, which was a large part of, when after I got my PhD, it was very hard to eventually find a permanent position. And playing the French horn also, it's not that I had talent of any sort, but I was tenacious in doing it. So I think tenacity in my own life, curiosity and tenacity have been really important factors in my life. And I strongly encourage to be tenacious and curious.
Those are two very important virtues, for
I would
sure.
also say, in modern society, one of the things that seems to be unbelievably lacking among public figures now is a sense of integrity. And I think that having integrity, believing in what you're doing and doing things consistent with your beliefs is unbelievably important. And it's hard to believe that many public figures now are acting with any sense of integrity. So I think that that's incredibly important. People, and in science also, there's an issue of, what are people's motivating factors as basic scientists? I think that for some colleagues, sometimes the motivating factor is not necessarily the work. This sounds nasty, but some people are very focused on having a lot of money. So you can build a career and sometimes be quite successful getting large grants. Uh, and that can be an object, and many universities now almost require you to get large grants to to get tenure or a job or whatever. But uh, I had a career in which I always had grants, but it was never very many and very few big ones. But one can have a career in which one doesn't necessarily, at least when I had my career, it wasn't critical to maximize the amount of money I got in grants.
Why do you think pe people have motives such as getting a big grant?
Why?
Yeah.
Oh, I think that many universities, that's what the deans care about. That's what the university depends on.
Mm.
Uh, that in some cases, that's the sine qua non. They just care about the amount of money that people get. And I have to say, in my university, in McGill University, uh, nobody ever told me you need to get more money for your grant. In the United States now, in many medical departments, uh, maybe in most or almost all departments, people have to cover part or all of their salary
Mm.
by getting grants. So get if you don't get enough grants to cover your salary, then you no longer have a job.
You're passionate about so many things. Is there one thing that stands out that you talk with the most passion? I mean, you talked passionately about many things. I'm just curious. So, is there something we haven't talked about that you're really passionate about?
Oh, I don't know that I could think of something
Okay.
particular.
Okay. And before I go to my last question, I know I said two, but then you gave me some interesting insights I wanted to ask on. Um, has your work influenced how you view everyday life, especially when it comes to chaos? Perhaps have you viewed everyday life or your relationships with people a little bit differently because of it as a result?
No,
Okay. That's
like,
fair.
not that I'm aware of.
Fair enough.
What one of the interesting questions, we're getting into questions of philosophy, is to what extent is everything determined or not? Do we have free will? So when you talk to your philosopher friends in other podcasts, you can ask them about free will.
I'm doing
So,
one on free will on the 20th, I
okay, there you go.
think.
So, in any case, I've talked about this a little bit with colleagues. Some of them feel very strongly that, okay, everything is completely determined. It's all physical, and there's no such thing as free will. But I guess in my own mind, uh, yes, everything is coming from someplace, but given the ion channels fluctuating open and closed stochastically and chaotic dynamics and so forth, what the paths are going to be, to me, is not, you know, any. It's hard to say that there's no range of free will, whatever that means. But you have to talk to philosophers to get much better answers than that.
If you had to summarize your life's mission in one sentence, what would that sentence be?
Can you ask that question again? My
Of
life's
course.
what?
That's so good. If you had to summarize your life's mission from the beginning to now in one sentence, what would that sentence be?
Whoa. I I guess I've tried to do things that I found enjoyable and to be good and fair to people.
Thank you so much. That was a great episode. I really enjoyed it. Um,
Okay.
we're gonna wrap this up around now. I just want to take a second moment to thank you, and I really appreciate your time, and I'm glad you enjoyed it too. Um, yeah, we are done.
Okay. Great. So thank you for inviting me and for guiding me through this.
That's so
So
good,
much appreciated.
guys. We hope you enjoyed, and we'll see you at the next episode. Bye bye.
Okay.